stage session. The first speaker is Anil Hirani, discrete vector bundles with connection in the first Chern question.
I'm grateful for the opportunity to share this with you. I must say I hesitated at first because, so Mark was a physics student. He was my student who was in the physics department, and he tried to teach me a lot of physics as much as he could, and but before he got to GR, he got an obviously good job, and so we never got to GR. So I was hesitating until I looked around, and I found that indeed some physicists, like the speaker who had to cancel yesterday, and Warner Miller, have thought about these things, have thought about GR using differential forms, and so I thought, okay, I'll be brave enough to tell you what we have and what we don't have, and perhaps get some suggestions from the physicists and others on how to proceed. Okay. So, as far as I understood by looking at a few things, that the differential forms version of things in GR is based on Cartan's trivialization of a vector bundle. So, you have a vector bundle and you have a trivializing open set, and you can define a frame on it. So there will be sections, 4 sections of that. There will be the dual one forms for those, and then from these you can construct the matrix, which is the connection one form matrix, and the curvature matrix. So I guess physicists might write that as A and F. Sometimes in math people write that as little omega and big omega. And so by the way, so this one comes from, you take the connection and it's a map from vector fields, cross sections to sections of the vector bundle. And so given any vector field X, the nabla of any section along that can be written in terms of the frame, and that's how you get a matrix. So the and the curvature matrix comes from writing this curvature applied to Ej in terms of the frame. So this is a function of 2, this is a function of 1, and it's obviously antisymmetric and has the right linearity properties, that it is a 2 form and this is a 1 form. This is a matrix of 1 forms and this is a matrix of 2 forms. So, so I saw in Jörg Frauendiener's paper and a short introduction to writing equations in GR using this formalism, and they introduce a form, a 2 form, 4 2 forms called L, and they decompose dl into S and E. E is called the Einstein 3 form, and this is called the Sparling 3 form, and there is a unique decomposition based on some requirement on E, and then apparently GR in equations for GR in vacuum correspond to E equal to 0, or that S is exact. So this is how far I can go with what I know in how this is done. So I'll tell you where we are going with this. Let's see, can I reach? So compared to what we've heard from the physics talks, which are focused on a very specific need, which is this missing portion of the spatial and time scales, where they need a specific calculation. This is very far from that. I mean, if ever this program progresses to GR, this will take probably many years. But I'll try to show you things in another field where we have done computations, and then let you be the judge on whether this will go anywhere or not. So it was pointed out to me that if you're interested in geometry, then and numerical PDEs, then GR is an obvious application. Yes. F is the curvature matrix, and A is a connection one-form matrix. Okay. So let me remind you that a connection on a vector bundle is defined by inspiration from the directional derivative in Rn by the two properties, that the nabla x applied to a section of the vector bundle. So you should think of this as a vector valued 0 form. This is C linear, so in C infinity linear in X, and has a Leibniz-like property, and R linear in this, and has a Leibniz property, with apologies to Mr. Newton looking down upon us. So we'd like to reproduce this basic property. The product rule is a very important part. So some examples of connections on vector bundles are the projection of the directional derivative on a surface in R3, for example, and the Levi-Civita connection on the tangent bundle of any Riemannian manifold, for example. And so there is a result that parallel transport completely determines the connection, and so we will work with parallel transport like we saw in Snorri's work. So you will see perhaps that this has the flavor of somehow Regi calculus or Wilson's lattice gauge theory, but these are two things that I know very little about. So I'm looking forward to talking to people like Warner Miller and Snorri while we are here to learn more and see sort of where these things differ. So our focus has been on the covariant, defining a discrete covariant exterior derivative, and building things which are consistent with that. So sort of truth in advertising, let me say what we do have and what we don't have. So what we have is we have a definition of a discrete covariant exterior derivative for vector bundle valued forms. And of course, we have a very sort of naive discrete vector bundles with connection. You will see how sort of simple this becomes when we start doing the actual examples. So this is really sort of child's play. And we have various properties about discrete vector bundles with connection, like determining triviality. So there are algorithmic results. We have linear algebraic type results on determining triviality, determining the maximum trivial subbundle. So I won't go into all those things. I'll just focus on the de Nabla and a discrete curvature 2 form I'll call F, and d Nabla square is F. So unlike the de Rham complex where d square is 0, the complex of vector bundle valued form d square is F. And so if you apply it to sections, d of d is f times the section, or wedge the section. So what we don't have, which we would need for GR, what we don't have is an understanding of the Ricci curvature, for example. We don't have the metric or pseudometric present explicitly. Although perhaps something with Reggie-like thing might be something worth considering. So we have an implicit way of dealing with metric, and I don't know how that will work out for pseudometric.
But I mean, at least to define the Riemann curvature, right?
Yeah.
You all you need is a connection. So
Yes.
presumably you have that.
Yes, yes.
In fact, the Ricci curvature.
Yeah, we do have the curvature 2 form.
Yeah.
Yeah, we do, and it's almost sort of laughably simple, and it's related to holonomy, and we just try to make it consistent with the D nabla that we have, so that we would get this. And we have a Bianchi identity.
Sorry, one question. What do you mean by pseudometric?
Oh, like what people use in GR, Lorentzian. Yeah. Yeah, that's right. So we deal with metric by using a primal and dual mesh in the scalar valued world of this. So after I describe what we have and don't have, I'll go on to describe our previous work on scalar valued forms and how that's discretized, where we do know how to deal with metric in a very sort of geometric way by using circumcentric dual meshes, just like Poincaré dual meshes, which generally are constructed using the barycenter. So I don't want to go into the adjoint picture because we haven't developed that for this vector bundle valued forms. So I would just say that, so there we have a metric and we know how to deal with it by sort of taking account of areas, lengths, volumes, angles, things like that. And I will show you the calculations that we have done in the past with that. Okay. Okay, so like I was saying, for several years we have been working on scalar valued forms, and this is our sort of recent foray into vector valued forms. So if you have scalar valued forms, then since you can add scalars which live in different vector spaces, the different tangent spaces, for defining the exterior derivative you don't need a connection. And so the sort of language there is exterior calculus. And so there's this thing called discrete exterior calculus, which we call DEC. Which several people have worked on, I have contributed to. It shows up in different forms in lots of methods going back to the 60s, like the Yi method, the marker and cell method, all the work of Bossevit in the 80s, Hipmeyer's work, all sorts of places, the co-volume method. But perhaps what we did, I guess, was to just sort of think about it in terms of cochains and coboundary operators, and introduced the dual picture and tried to carry it as much as we could. But so there is a connection between discrete exterior calculus and finite element exterior calculus at the lowest order. Finite element exterior calculus, which people have been calling FEEC. So so Feek is very, very flexible, has ability to approximate things at any degree polynomial order, and is being developed further and further, as we have seen. And so DEC gives you very little things to play with, and somehow in developing a new discretization, that's helpful because there are already too many things to sort of pin down, and it helps to sort of play around with these sort of a toy calculus to get a geometric understanding. So I'm not saying that yeah, so it's not a competitor, it's just at the lowest level, it's just different, let's just say. At the lowest, it's very combinatorial. There's a very specific connection between the two. Like at the lowest level, when you write down the lowest order polynomial Whitney forms and write down the mixed form for the Hodge-Laplace problem, and you do the same thing for DEC, you see that the matrices are identical in shape and form. The mass matrix is the only place where you see the difference. The mass matrix in the lowest order Feek discretization would be not diagonal but sparse, whereas the DEC one will be diagonal. So in principle, the sorts of things that perhaps Ari said, if Maxwell is one of the stepping stones and Yang-Mills is another one, but as Ari talked about Maxwell's, so whatever you can say with the lowest order elements using Feek for Maxwell could also translate potentially. I don't know, because I haven't done time-dependent computations in Maxwell, but I have done curl computations. So curl of electric field is lambda times electric field. So E is a one form, and so that, like on a square, should have discrete eigenvalues, and it shouldn't have the divergence should be 0 for the vector field that you compute. And so we have been able to sort of reproduce at more approximate order that Feek, that computation that Feek can do. So in principle, if Maxwell is one of the stepping stones to GR, I mean, at least we are on the right track, perhaps. Okay. So now the sort of the main part of the talk will be this discrete vector bundle with connection. So I'll define what it is, and it takes shorter to define it than to maybe write it down. Because a discrete vector bundle in the way we define it without a connection is very boring, and it's only the connection that makes it interesting. Then I'll talk about how the Nabla operator is discretized on sections, so on vector valued 0 forms, and how d Nabla is defined, and the fact that the pullback of d Nabla, so pullback commutes with d Nabla, but pullback under what? So these will be vector bundle maps, and there will be an underlying map of the underlying space. So I will say that all of that in examples using drawings with triangles and tetrahedra. So one nice thing about DEC and this sort of stuff is that it can literally be explained in a high school class. There is sort of games you play with, numbers on triangles and numbers on tetrahedra. So and we have a wedge between vector valued and scalar valued forms, and the wedge commutes with pullback, but it has the same restrictions that the wedge product has in our DEC, which is that it's anti-commutative, it's natural under pullbacks, it satisfies the Leibniz property or sort of anti-derivation property, but it's not associative. Okay, so that, and then maybe I'll do this, and then talk a little bit about the computations with the first Chern class. So the first Chern class computations are because it's a topological quantity, so the order of the method shouldn't matter too much, and this is just a test to test our ideas. It's a topological invariant of vector bundles, independent of the connection. So I will sort of define the discrete version and show you some computations with that for a line bundle. So on a surface, just thinking the tangent bundle of an embedded surface as a line bundle, complex U1 bundle. So this is a nice test because the first Chern class of the tangent bundle of any surface. So that's a form. It's a two form. So you can feed it the surface oriented in a consistent way, and what you will get is the Euler characteristic of the surface. So this is an integer, and so for example for a sphere you will get 2, and for a torus you will get 0. So torus will be the only one where you will have 0. Okay, so since this d nabla is built on top of DEC, and all of these wedge operations are built on top of DEC, the same sort of principles apply. These are hard. I mean, I don't know what to call them. It's just sort of way of working that we have been following. So the way of working has been to define discrete operators satisfying the properties that we know as much as we can of the smooth world. So this is usually, so the sort of inventiveness is in figuring out what things to use, and to a large extent for the metric free part we get for free things from algebraic topology for the scalar valued case, but it doesn't help us in the vector bundle valued case. So this is not hard. The proofs are not deep by any chance. The sort of the difficult part is the analysis, which is still largely open. So like for example, if you want to prove that the L2 norm of the Poisson's problem converges for one forms in 2D, that's open. For the zero form case, Gantemur and his student have a recent paper. For the n form case for 2D and 3D, Bredzi, Fortin, and Marini had a paper. Yeah, that's right, in 2006 or 7, which can be interpreted as a proof of convergence for the Poisson problem for DEC. And the zero form case, as I understand, the numerical order of convergence is second, but their proof is conservative, and it's only able to show that it's order H convergent. So there's still room in the analysis, and so I mean in retrospect. So anyway, so we are starting to think about. So we did some stuff on that, trying to use a variational crimes framework and the Bredzi approach, and got somewhere. But we are trying to restart that, hopefully with some of the people who are here. So after my student graduated 4 years ago, who was working on this, we didn't really work on the analysis, but I think now we'll get back to that. And then, so the hardest part is to implement, test, measure the error. So this is harder than you think, because you have to find a physicist or an engineer who's interested in using this. I mean, the typical reaction of an engineer is, why should I use it? What can you give me that I don't have? So without analysis, you can't really tell them that you have this that they don't. Luckily, I was able to find collaborators who liked DEC and then have approached me. So we've done some work on Navier-Stokes, for example. So finding an engineer who's interested, then sort of understanding their domain, then sort of going deep into the test cases that they use, then measuring the error. It's a non-trivial programming task. You have to implement, and so that's where all the hard work is. And I expect the same to happen with this vector bundle valued calculus, because it's not systematically implemented. So we did have, so with Nathan Bell, who's at Google now, we had a library called PyDeck, which is a Python implementation of both the lowest order Whitney forms, so finite element exterior calculus and discrete exterior calculus, and we've been using that in our computation. So I also do a little bit in computational topology where you may not have a metric and you just want to work with the boundary matrices and abstract simplicial complexes, like if you want to do something on not an embedded complex but just something defined abstractly like a Mobius or projective plane. So we've used this tool to do experiments in that and get results. Right. So, okay, so the first thing, this decommuting with pullback, this is also true in the scalar valued case. And I want to just sort of point out why that's important. Why, because I will be making a big deal of that. I'll do the calculation for the vector bundle valued case for a tetrahedron so that you can see all the pieces involved. What does the pullback mean in that case, in this discrete case, and why it commutes and commutes under pullback under what. So it's important because, so why decommuting with pullback is important in general. So for example, the chain rule, so the decommuting with pullback in the scalar valued case would be the pullback of a form, D of a form is D of the pullback of a form. So for example, let's say you are talking about chain rule in calculus. So this is the simplest application of pullback commuting with D. So you've got a map phi from, let's say, reals to reals, and you have a real valued function here. So pullback, so let's do that calculation here. So pullback of df is supposed to be D of pullback of f, which is D of f composed with phi. So you would write this as d by dx of f of phi of x. So on the other hand, this guy pullback of df at a point x applied to a vector v will be, you send the vector over there, evaluate it there, right? So it would be take differential of f at phi of x and compose that with differential of phi at x and apply that to the vector. So since this is an arbitrary vector, let me remove that. So this is the relationship for the thing on the left. But what is this? This is phi prime, sorry, f prime at phi x times phi prime x. So when you write the chain rule, what you're using is pullback commutes with D. So maybe one lesson is that, let's say you're defining some discrete derivative, you had better be clear about what is, for example, you might do, okay, by discrete, more generally, let's say you're doing non-conforming finite elements, your space, your discretized space is not a subspace of the bigger containing function space, so that your derivatives are not restrictions of the true smooth derivatives as you would have in a conforming case. Then you will need to define something specifically, and so you will need to be careful about whether it commutes with pullback or not, for example. So I mean, this is just my guess because I'm not a non-conforming finite element expert, although I'm learning from people who are also here. So this is a fantastic series of conferences, and the whole meeting, it's like everybody whose papers I've read is here, and others, so it's really exciting to be here. Okay, so the other useful thing about decommuting with pullback is that cohomology groups are invariant under diffeomorphism. So there are many situations where decommuting with pullback is important. Okay, so let's now start talking about DEC, discrete exterior calculus, a little bit. So my plan was, since I'm going to do the pullback stuff and so on, and carefully show you the de-Nabla calculations for the vector bundle case, I won't do that for the scalar valued case, which is easier. But what I do instead is just tell you the sort of setup and then show you some numerical results. So in DEC, the focus is on what you would call degrees of freedom in finite elements. The focus is on cochains, which you can think of just as, so you have a simplicial complex X, and its relationship to the true manifold might be that you've sampled the vertices of the you put some vertices on the manifold, and you approximated that with some piecewise linear simplices. They don't have to be embedded, but you can embed them. So you've got a simplicial complex, let's say a triangle mesh or a tetrahedral mesh, and you can just think of, so it builds on real valued cochains. So you can just think of them as numbers on vertices, numbers on edges, numbers on triangles, numbers on tetrahedra, things like that. So then D is just the coboundary operator, and you will see it in action, so I don't need to say, and so that comes from algebraic topology. The wedge product is just the symmetrization of the cup product. So these come for free from algebraic topology. You don't really need to define anything new. So you get automatically that D of alpha wedge beta will have the anti-derivation property. You get that alpha wedge beta will be minus. So this is a K form and this is an L form. Is K times L beta wedge alpha. It's not associative though, because somehow the cup product is symmetrized by taking it at different points. In the limit it is associative, and it's associative for closed forms, but it's not associative. Okay, so then there is an adjoint picture. Which is something the algebraic topologists didn't give us, because obviously they don't care about geometry, they care about just topology. So, well, geometric topologists do care about both, but like low dimensional topologists care about geometry. But anyway, so algebraic topology doesn't hand you how to deal with metric. So for that there is an adjoint picture. So just for this coboundary operator you can define an adjoint, you can define a Hodge star. So we do that using primal and dual meshes. The construction of which is implemented in PyDeck, for example. And you don't need an explicit representation for the dual mesh. You just need measurements of areas and lengths and volumes with an appropriate sign. And you can do that for as long as the mesh is Delaunay without problem. But we've seen now numerical results that even for quite bad meshes, you can get the correct convergence. So then there's a Hodge star matrix which captures the metric. It's a diagonal matrix. So this would be the mass matrix in finite elements. And so that's the connection to Fick, that it's only the mass. So although Fick people typically don't think of defining Fick in this way, but at the lowest order the degrees of freedom are exactly the vertices, the triangles, the edges and tetrahedra and so on. And so for Whitney forms, Whitney 1 forms are associated with, let's say, on a triangle, are associated with an edge, also on a tetrahedra. Whitney 2 forms are associated with the triangles, and so on. And so it was a great success one. I mean, when Arnold Winther were able to systematically extend Whitney forms and then sort of unify all of the different finite elements that have been used, many of the finite elements that have been used in mixed finite elements, using the exterior calculus framework of Fick. Okay, so before I show the results, I want to just write down one thing. Okay, so you have to discover what does it mean if you want to do pullback under a map. In the smooth world, the map doesn't need to be a diffeomorphism. Pullback commutes with D as long as the map is smooth. So what's the analog of smooth maps in this business? And long ago we used to think that it's simplicial isomorphisms, but if you think a little bit more, it works for general abstract simplicial maps. So an abstract simplicial map so it's a map from one simplicial complex to another. The complexes don't need to be embedded or geometric. You can be just specifying them with vertices that here are the triangles, here is how they are glued, and so on. So this map maps vertices, which I'll write as that, vertices of K to vertices of L, such that if some vertices span a simplex in K, the image spans a simplex in L. So this prevents vertices from running away too far. So it has at least this feeling of continuity, and this is what plays the role. So for example, collapse is okay, because after all, a smooth map need not be a diffeomorphism, doesn't have to be invertible, so you should allow that. And so these maps allow a collapse but prevent things from going too far. And so this is the kind of map which plays the role of smooth maps in a combinatorial theory. So for example, if you have vertex V0, V1, V2, and the triangle is included, and you have a map phi such that Vi goes to Ui, and you have U0, U1, U2, then this is not an abstract simplicial map, because these two vertices span an edge and they don't span an edge here. So somehow it keeps things in the same simplex nearby in the destination. So here's one which is an abstract simplicial map. So suppose, and this one involves a collapse. So let's say this map phi maps vertex V0 to U0, V1 to U1, and V2 to U0, V2 to U1, sorry. So then this is okay. This is still a valid abstract simplicial map. And when you pull back under this, if you want d nabla to compute, it kind of commute d to commute with pullback. You can see what you need to do is that this value should be the same here, this value should be the same here, and this value should be the same here, so that when you take the discrete d of this, which is b minus a, if you pull back that appropriately, you'll end up with a b minus a here, b minus a here, and 0 here, and it will give you what you need. So, but I said I don't want to do the pullback computation for this one, because we're going to do one, I hope, for yeah. So luckily the algebraic topologists were kind to us, they gave us almost everything that you needed. So we will say that the pullback of a k cochain on a k simplex, so vertex 0 1 dot 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 k is the value of alpha on the image. So if the image collapses to a lower dimensional thing, then for dimensional reasons that should be 0. So collapse implies 0. Okay, so I think now maybe I should just show you the results. From the deck computations, and then show you some of the stuff that we can do in extending this. So here's a convergence of the mixed, well, for k equal to 0, mixed is the same as standard, but the mixed form Poisson equation using discrete exterior calculus. So the number of triangles is mentioned in some of them. So let's see, this one is k equal to 0. For k equal to 1, the degrees of freedom are the edges, but last night we didn't have that information. So k equal to 1 corresponds to the Laplacian on 1 forms. The degrees of freedom are the edges. So I mean, just this computation alone requires a lot of work to get to this place. And in retrospect, it might have been easier to just work with a good analyst and prove it then. But then we still like to program. So when you're programming, you feel like you make regular progress, right? We were just talking this morning with my roommate, like if you work one day, you made some progress, but in math, you can work for 6 months and make no progress, or seemingly. So anyway, so then this is in 3D. The first one is scalar, going up to 2 point something million tetrahedra. The second one is Laplacian on 1 forms on a cube. So the first one homology is trivial. This is on a solid torus. So you have to generate a solid torus. You have to work with it. And due to the limitations of time and computing capability, Kaushik, my student who graduated in 2015, was able to do only a few levels here. So it's showing all the right convergence error. This is continuing for 2 forms, and so this is a solid annulus. So it's a ball with a ball removed. So these are non-trivial computations. You have to compute the differential form, the harmonic form also. So this shows, so it looks the same, so but it's not cheating. This right-hand side is finite element exterior calculus error calculation, and the left-hand side is discrete exterior calculus error calculation on the same problem. So this is on a square 2 form. The bottom figure is the codifferential of the 2 form U. The 2 form is on the top, and the 1 form in the mixed form is on the bottom.
So this is the previous picture, you have a case where you were converting to first order, and other ones where you're converting to second order.
Yeah, that's for scalar it is second. For 1 forms it's 1.
And it's the best you can do
With DEC, that's the best we can do. With FEEC, you can go to wherever you want. But okay, so you might argue that, well, so suppose you're doing a surface problem, and you or some non-smooth problem, sorry, not non-smooth, but non-flat problem, and you approximate your surface by piecewise linear things. So then there will be a geometric error, which will be, I think, O of h square. But there are ways to get around it. So I'm not saying that there is any advantage to DEC. Like I said, it's just different. Here's a computation of harmonic forms, which are localized to wherever you want to localize. So this is also done using DEC. Okay, these are just the boundary conditions and the solutions. So here are some results from Navier-Stokes with my collaborators in KAUST. So this one, okay, so I should say a few words about Navier-Stokes. So the Navier-Stokes has this convective term u dot nabla u. So that if you write in exterior calculus can be written in terms of the Lie derivative and d of something, and the Lie derivative can be reduced to a contraction. The contraction we can write in terms of wedges and Hodge. So we are able to, so that's what we used. We used a primal dual mesh. We discretized the Lie derivative using contraction, using wedge and Hodge, and these are the results based on those computations. So I trust my collaborators who worked in CFD for a long time for picking the right test. So this is apparently a famous test by the author. The red dots are that famous test. It's a driven cavity, so it's a square with fluid filled in it. The bottom and the sides don't allow any fluid to go. The fluid is flowing on the top. There's no flux across that. It has unit velocity on the top, so that will drive the fluid inside to form a vortex. And this is at a certain time. You look at the x component and the y component of the velocity. This is what they did, and so we wanted to compare to steady state. So this is time evolution. This is Taylor-Green vortex with periodic boundary conditions. Viscosity is written there, about 50,000 triangles, and this is at time t equal to 10. This is a flow through a planar pipe with a quadratic profile at the entry and no flux through the top and bottom. And this is the analysis, the numerical convergence, which matches with what Nicolaides did in the co-volume method.
So these are two-dimensional.
These are two-dimensional. So the whole work is for 2D Navier-Stokes. So we wanted to do, for some reason, 2D Navier-Stokes on a surface. So imagine a very smooth surface on which the fluid itself is thought of as a two-dimensional thing.
So for the time evolution, I mean, is there any of these differential form stuff done in that?
No, not in this.
The fact that, you know, time evolution is just, you know, plain old, you know, Runge-Kutta or whatever.
No, it's not Runge-Kutta.
Spatial things are done by you know, discretizing using the.
Yeah, in principle, exactly that. It's not Runge-Kutta, but it's something carefully picked from the literature. Like there's a paper by Perot on similar things. So it's a predictor corrector type method. So in those days, we were not focused on time, and this is why this workshop is happening, to bring the time people and the spatial people together.
Yeah. No, but that's fine. I mean,
Yeah.
but basically the form stuff
Is only for the spatial. Yes, yes.
And then time evolution
That's right.
is, you know, whatever your favorite method.
Exactly, yeah. So semi-discretization, like Ari was saying.
Yeah.
So you could do exactly what he was saying for the Maxwell's, for example, and get that form and apply variational methods if you wish. Yeah, symplectic methods. I mean, I'm somewhat familiar with symplectic stuff and variational integrators. I was there when all of that was happening. I wrote a master's thesis, but I left that field. So I'm aware of its advantages and the fact that the two should combine. It's just, yeah.
But for these purposes, what you mostly have is a spatial method.
Yes, yes.
And then
The time is whatever you
done
have.
by whatever your favorite time evolution
That's right.
is.
That's right. Yeah. So this is a periodic shear layer. This is inviscid, and the time step is written there. And this is computing the kinetic energy integral on the whole domain and measuring it with respect to the mesh length. This is at the bottom figure is, I think, at time t equal to 1.2, time step of 0.001. This is Taylor vortices, and this is now studying what happens when you make time steps smaller and measure the relative error in the kinetic energy.
Here in this evolution, you have on the spatial side, you have deck and
Yes.
your triangulation.
That's right.
The
Yeah.
triangulation is kept fixed
Yes.
all through.
Yes, it's Eulerian, yeah. Yeah.
What are the elements in velocity graph?
So we use the dual one forms for velocity, And so hidden behind, there is actually Whitney interpolation needed to deal with the wedge product. So the wedge product is between primal 1 forms and primal 0 forms. It's a vorticity formulation. No, it's on the entire dual edge. It's a dual 1 form. The velocity is a dual 1 form, and it's so it's the vorticity is something that lives on the dual 2 cochains, so around vertices. The velocity is on the dual, so the d of that will give you something on the dual region. Yes.
So I could think of dual edges in this case as being multiple edges. So I think of this as being like the velocities that you each did, or would you think like Ravi or
Yeah. Would it be Ravi-Thomas or Whitney forms, one or the other, right?
Could you draw a little picture of the simplex and the dual simplex?
Oh, yeah, sure. Yeah. In fact, I might have that on the slide here. So here's the picture. So the velocities live on the red edges. Oh, okay. I guess we should move on. I haven't gotten to d nabla. So sorry, Doug, are you okay if we talk about this later? Right. So velocities live there. The vorticity is living in the dual 2 region. So anyway, so just quickly flip through. I just want to show you one thing. So for that computation on the previous slide, this is a comparison with structure preserving discretization paper of Pavlov et al., who get 2% error on the same mesh, and we have 0.003% error. And we did this because the reviewer said, but what about that? And these are things on a sphere, other things on a sphere. There's a vortex on the other side, and it's supposed to just rotate, and it does. So sorry, we have to sort of get to, so there's mass conservation, and my collaborator is working with others on trying to do new physics, like flow past an obstacle using this code on curved things. Okay, so we can switch that off now. Okay, I guess I won't have time to do too much on the vector bundle stuff, but let's see how far we can get. So a discrete vector bundle with connection is, so let's say we call it E, it's just a triple. It's a simplicial complex X, a vector space V associated with every vertex, and like Snorri had coming, I mean the kind of thing that Snorri mentioned, these are there are parallel transport matrices on the edges, only on the edges. So this is nothing new. This is completely standard, and it's what you do with it in terms of d nabla that's new. So a vector bundle valued k cochain is just a vector which is associated with a k simplex, but it's made to live in a trivialization of that simplex based on a basis that you select for the lowest vertex of that simplex. So when you do these parallel transport matrices, these will have to be computed by solving the parallel transport equation, and it doesn't depend on the coordinates, just depends on the basis you pick at the ends. So I'm saying that the calculation that you will do will be based on the vertex, the lowest numbered vertex of that simplex. So okay, let's at least try to get to, if you have a vector bundle valued 0 cochain, so you have a section, i.e. just a vector living at every vertex, then what should nabla be? Nabla of S, well, it's the vector valued 1 form, then obviously its value on an edge should be somehow a difference of the values. So you should take the value at 1, and you would like to compute its difference with value at 0, but because they live in different places, you have to move them by the parallel transport matrix from vertex 1 to vertex 0. Okay, so I guess I will just get to d nabla. and just state the properties that I've mentioned. So we are going to put out a paper soon. Okay, so what's so if you have a k cochain, then the nabla of that, you want to compute it on a k simplex. So it's almost like, I mean, I really want to get this across because this is the main idea. And this, by the way, appears in the field of synthetic differential geometry and in the work of Anders Koch. What we've done is generalize this and extended this and then made it work with various things like curvature. So d nabla, it should be, it's like a boundary operator, except that let's say you have a triangle and you have alpha living on edge 0, 1, alpha living on edge 1, 2, and alpha living on edge 0, 2. So notice that only the far simplex doesn't contain vertex 0. So when you're trying to do the boundary operation, you have to basically add and subtract things based on which vertex you are deleting. So you do the normal boundary operation, but you take the far simplex and you move it to 0. And now everything is in the same vector space, and so that computation can be done. So what you do is you write down, you take the one which is living on the far simplex. So the far simplex is the one that doesn't include the vertex 0. You move it, so this guy lives at its lowest vertex, it lives here. You move it along this edge using this parallel transport matrix, so from 1 to 0. And the rest is just a boundary matrix. So with this D, you can prove all those properties I mentioned. You get a curvature definition which is consistent with this D, and I'm afraid I have to stop here, and I'm happy to talk about these sort of show you some calculations and show you those results and the Chern class computations. So, sure. In any simplex, let's say you have a tetrahedron. There is a far simplex, a far face, the one that doesn't include 0, far from 0. Yeah. All the other triangles have the vertex 0. This one doesn't. So when you want to do a computation of vector addition or subtraction, you have to do that at the same vector space. Luckily, all of these triangles, the vector valued forms living on these triangles already live at 0, so you can do the usual boundary operation on them, but this guy doesn't, so you have to move it to 0 via the parallel transport. And so sort of the fun is in making that definition then work with the right curvature, then using it for the Chern class and seeing that you get D square is F and defining a wedge product. So there's quite a bit that one needs to do after that. Yes? Yeah, the matrices move everything around and you get the right thing. And it transforms in the gauge. So a gauge transform is a choice of a matrix at every vertex, and the D transforms in the right way that you would expect. Yes?
Yeah, so, I mean, once you were, in the earlier stuff, when you were restricting to forms, the only sort of machinery that you had, sort of, forms D and Schubel, and so,
Right.
Things that could be written in terms of that, great, you were all set.
Right.
But now you're introducing vectors and covariant derivatives.
Right.
So now, it would seem that you should get for free the entire apparatus of tensor bundles of type PQ, for any Q. So So is that
Well, tensors have been hard, even general tensors have been hard, even for the scalar valued case. Basically, these forms only capture, the cochains only capture antisymmetric tensors, forms. Even vector fields have been a challenge in the past.
right? Well, so that I get, but now that you have vector fields,
Yeah.
right? So now, I mean,
But for example, I don't know, if you hand me a vector bundle, I don't know how to recognize whether it is a tangent bundle or not. So you give me the simplicial complex with some vector space of the right dimension, and you give me the parallel transport matrices. I don't yet know whether.
this is some arbitrary vector bundle, not
Yeah.
necessarily the tangent.
That's right, right. And so the computations we did was with the tangent bundle, where we computed parallel transport matrices on the sphere and on a torus. Yeah, so the idea is that somebody hands you a vector bundle, possibly the tangent bundle with Levi and a connection, Levi-Civita connection. You sample the underlying manifold. Those are your vertices. Then you travel along whatever paths you pick, and that combinatorial information tells you who's connected to what. You compute the parallel transport on those edges and put them on your simplicial complex. So that's the data you start with.
Yeah, okay, but,
So-
but I mean, you have the tangent space, you have the cotangent space. So
Yeah.
now arbitrary tensors are just, tensor products of those. So it sounds like
Well, like there's no tangent space at the vertex, for example, right? I mean, unless you take this vector space and you have some way of recognizing. Yes, if you take a tangent bundle and discretize it, then you have the vector space, which is the tangent space. So yeah, perhaps in principle, you could do more than we were able to do with the scalar valued case where we didn't have such a thing. Yeah. So there what we did was we had piecewise constant vector fields, and we were able to go back and forth between forms and vector fields using flats and sharps in some way. Yes.
Yeah, thank you. Concerning your fluid simulation, so in this case, at the continuous level, you have preservation of the volume of the fluid, right?
Yeah, there's mass conservation, vorticity conservation.
Ensure the preservation of all the LP norm, which is too much for a discrete
I don't know about.
model. So,
yeah.
so do you have an analog of this volume preservation of preservation of the LP norm at the semi-discrete level?
That would be nice, and I don't know the structure of the semi-discrete equations, like for example, are they Hamiltonian in the inviscid case or not? That would be nice to know. Yeah, no, I don't know. Yes.
So what does the jet wedge product correspond to in phi?
Uh,
That's one of the things that isn't really in the
Yeah, so in phi, you would just take the Whitney forms, for example, in the lowest case, and do the usual wedge, right, on the.
But that would then no longer be a wedge.
That's right. Yeah.
So usually that's what you do is you do a wedge. You insist that the wedge is the Whitney form, is exactly the wedge product acts into the Whitney form, and then you lose steady by the surface, there would be wedge there.
Okay.
Is that equivalent? I don't know.
Do we what? Oh, about the question about when you project it back? This I don't know.